Okay, here's a little experiment we're going to carry out, or a couple of small experiments, and it was in regards to a video that WhatsApp showed. He placed a tape head across his scope probe, sent an AC current through an air core coil, and he would get a voltage at one end. That voltage would slowly die as it went towards the other end of the air core coil. The current he was putting into the air core coil was AC, so it should have been much the same end to end. So what we're going to do here, once again we're using our favourite microwave oven transformer secondary coil, which is also an air core. I have my old tower coil wrapped around a bit of pipe. That red lead coming out there is just the end that I've fed back through the pipe, so as I can have my scope probes all at one centre. So I think we can explain one thing that WhatsApp is seeing, but not the other, and that is why he's seeing a high voltage developed at the end of the coil from his tape head, which is just a head out of an old tape recorder, but in the middle he gets nothing. And there is also a lot of people believe that the magnetic field in the centre is some sort of blotched wall where it is neutral, nothing happens, blah blah blah, which is not the case. The electromagnetic field is going to be strongest where? So we're going to have a stronger electromagnetic field, which is the magnetic and electric field at one end, and the other end, or is it going to be in the middle? That we can find out. That's not too hard, simply by sliding our secondary coil along our primary coil here. We can see as to the highest developed power from the secondary coil is, and across that secondary coil I have a 220 ohm resistor, just a small one because not a lot of power, being air core, and also have a cap across that coil, this one here as well, to smooth up the waveform a bit. That is a 16 UF cap that does nothing but smooth the waveform up, and we'll disconnect that later on so you can have a look. And the interesting thing I've found is with the power phase on this coil compared to the power phase on this coil. I would have thought that the phases should have been in line, but it appears they are not. Right, so we have a 10 watt 1 ohm CVR here. This is just to show us that our voltage across the coil, current through the coil are in phase. We're only at 50 Hertz. We're running somewhere around 4.5 volts, but this is an old DC transformer that I've ripped the rectifier and capacitors out of, so it's now an AC one, so the voltage will be a little higher, the RMS voltage, due to no voltage drop across the diodes. And that is basically our setup. So we're going to just slide this coil, the secondary along the primary, and see where we develop the highest voltage across our resistive load there in the secondary, in regards to position of the primary. But first we'll have a look at the voltage and current, so as you can see that they are indeed in phase, and I will switch on the transformer now. Oops, we will have to turn that down. Okay, so you can see our voltage and current are fairly close to being in phase with each other. We're only running at 50 Hertz. We have 1.2 volts across our 1 ohm CVR, so we're running at a current of 1.2 amps. And we have 5.8 volts RMS across the coil. So it's 5.8 volts times 1.2 amps, and it is our power in watts being dissipated across that coil. So what we're going to do now is I will shift channel B of our scope here across to our secondary coil, and like I said, because we're dealing with air cores here, alright, so our secondary coil is now at one end of our primary. We most believe the highest electromagnetic field is, and in the middle there is supposed to be this null blocked wall, nothing field. It's supposed to be neutral. So we have 460 volts RMS across our 220 ohm capacitor inductor combo. Now we'll disconnect this cap, and you can see there that the waveform is quite messy. I have in actual fact hooked that up the wrong way around, so I'm going to have to invert that channel. Alright, so now it's correct. Now what you can see here is a phase shift of almost, very close to 90 degrees, which in theory should be reactive power, and if it's reactive power, in theory we shouldn't be able to use it, although we're dissipating that power across the 1 ohm resistor, and also of course our cap and coil. So very interesting in itself. What I'm going to do now is I'm going to slide this coil to the centre of the coil like that. So I'll move it back, and as I do that I'll let you watch the scope. And now we're about the middle. So now we have 640 volts RMS across our 220 ohm resistor, and our coil is now in the middle of our primary coil. So once again, at one end, about 460 millivolts RMS across our little 220 ohm resistor there, capacitor combo, and move our coil to the centre, which is about there. Now have 640. So we've increased the power being dissipated across our little resistor there by about 30%. And of course, if I slide him down at the other end, like so, we can once again see we have 440, 460 millivolts RMS across our little resistor down there. Like I said, we can disconnect the cap. That just makes the waveform a little messy. Also drops our RMS voltage a bit, because I spent a little bit of time choosing that cap, so it gives us the best performance. So in this case, our secondary coil here is telling us that most of the electromagnetic energy across our primary is in the middle, contrary to belief that the middle is supposed to be some null void field. To me that's understandable, to some it's not going to be, and might be quite surprising, but I've always known this to be the case since some tests very early on. What I don't understand is why it is 90 degrees out of phase with the primary coil, which is showing us reactive power really, although we can still dissipate that power across our resistor. coil and our capacitor. As far as I know, most transformers at 50 Hertz, which is very low in the frequency, would be in phase. And like I said, the cap really makes no difference. I must have a loose wire here somewhere. Other than the fact that the waveform gets a bit messy and our RMS voltage drops down. And if I hook the cap back up to smooth things up a bit, we can see that the phase doesn't change. So our voltage and current on the input is in phase due to the low frequency and the air core coil, but for some reason our secondary is 90 degrees out of phase. So there you go. So what we're going to do next is have a look at what What's Up did, and going to put our tape head across our scope probe, and we're going to probe along the coil. Now I get a different result than he did. As I said, he would get voltage showing on his scope at one end and that would die off, and he would get absolutely nothing down the other end. So I'll show you what I get, and then we'll swap over to this little inductor here and we'll have a look again, and then I'll see if I can explain as to why it's doing what it's doing. So we'll be back shortly. Okay, so we have our little tape head on the end of our scope probe, and we have our voltage across our coil, and as we already know, the voltage and current is in phase here on our primary coil, and as we've seen on our secondary coil, it was out of phase by 90 degrees. Why, I don't know. So we're going to give this a try. So we're just going to place our little tape head on the end, and once again you can see that even though the magnetic field should develop, in this case along with the voltage and current which are in phase, once again it is out by nearly 90 degrees, and that is with the tape head right on the end. Now as I move this towards the middle, and we don't have to go very far, out there you see we get nothing on the scope, and as I move towards the other end you can once again see we start to develop a voltage across our little tape head once we're at the end of the coil, which is also 90 degrees out of phase. So a large coil is telling us the strongest electric and magnetic field is in the centre, and this tape head is telling us that the strongest point is at the two ends, and it is still 90 degrees out of phase. Now the 90 degrees out of phase thing I can't explain, because our current and voltage are in phase in our primary coil, which means the electric and magnetic field should also be in phase, and thus our secondary should be in phase, but for some reason it is not. So what we're going to do now, I believe I can explain both things in regards to What's Up video, where it shows a voltage at one end and then it dies down to nothing at the other. I think there's a reason for that. So what we're going to do first, we're going to take our tape head off, and we're going to put this small inductor on our scope lead, and we'll have another look. So I'll go ahead and do that, and we'll be back shortly. Alright, so in this part of the test we're going to use our little inductor here to have a look at the field across this coil. One thing we should mention before we go any further, although this is an isolated transformer and has no common ground as far as the input goes and as far as the grid goes, once we hook our scope probe up to what is the ground side, as the scope has a common ground with all the rest of the equipment and the grid, our secondary on our transformer also now has a common ground. So everything should be in phase, but as you'll see once again, it is not. So we've got our little inductor here. The yellow channel is across the coil, the primary coil, a big long one, 5 volts per division, and our blue channel, channel 2, is across our little inductor we're about to scope the primary coil with. So as I place this on the end here, you can see we get a nice voltage across that coil, and as I slide it towards the middle, that drops off very rapidly, and we basically have nothing there, and we've only gone 3 inches in. So continue to slide along the coil, and we are now in the centre, where before we were getting the most output from the coil that was around our primary, and from this one here we're getting the least amount of output, using nothing. This little inductor here doesn't even have a resistor across it like that one did. So diddly squat in the middle. As we move towards the end, you can see once again we start getting a voltage across our little inductor, and right at the end we have 312 millivolts RMS. So opposite to what we've seen with the big one around our primary, whereas the centre gave us the best output and the two ends give us the least. In this case, with the inductor just on one part of our coil, we get the most on the ends and we get the least in the middle, nothing. So if I turn this sideways like this and place it, say, one end at the edge of our primary, you can see we get a voltage across it. Now as I move that outwards, like so, we'll have a look at the change. There you go. So we now flip that over 180 degrees. So what's happening in this case is the magnetic field that comes out of the end of our coil curls around, heads back towards this end, and vice versa when our wave goes the opposite way, or our current alternates in the opposite direction. We are seeing the magnetic field coming out of the end, going straight into the steel core out this side and curl back, which gives us the waveform that is before the voltage current across our primary coil. So when we shift this back level like that, and this waveform jumps 180 degrees, we now know that the magnetic field is coming out, going straight into this end of our little inductor first, out the other end and down there. So that's showing us the curl of the magnetic field, and on one side we can get one polarity, on the other side we get the other, simply because the magnetic field is flowing through one end of our inductor first and exiting the other, and we're simply swapping that around, which gives us the reverse of what our phase is compared to our primary inductor. So the other thing want to have a look at, the electric field is supposed to be rotating around this inductor, and we can pretty much well say that in the middle of this primary coil the electric field will be fairly straight and it'll be spinning one way at one half of the AC cycle and the other way at the other half. So if we have, like our first coil we used, around the whole inductor or the whole primary, we can envision that the electric field would indeed induce an EMF across our secondary coil, because it would be flowing around that coil of wire all in the same direction per half phase. So one would think if we put the coil on the outside like this, the electric field is not going to stay there, it's just going to be a pain in the ass. Anyway, it just doesn't want to do what it's told. If I turn that around a tad like that, it'll be better. Okay, so one could imagine that electric field going around the coil would cut into one side of the conductors in that inductor and then cut through the windings that are now going in the opposite direction because they're on the other side of the inductor, and we would have nothing. But we do. So the only thing that could be inducing that EMF across that inductor now is the magnetic field shooting through our windings that way, and not the electric field that is going around our primary coil here. So interesting, but that's what we've got so far. In our next video we're going to be looking at the field inside the coil, and as we've seen on this one, if I place our coil like this, get a voltage like that, and as I move it towards the middle, our voltage dies in the butt, and towards the other end our voltage once again rises across that secondary inductor. But what will happen if we slide this little inductor through the middle of the coil? Will it get weaker in the middle as it does on the outside, or will it be the same all the way through, or will it be weaker on the ends, stronger in the middle and weaker on the other end? So that's what we're going to be looking at in the next video, driving it with this power supply here, and then we're going to switch over to our function generator here, and we've seen the current we're using at 50 Hertz through this coil in the start of this video when we had the CVR on there, and we'll hook the CVR back up again. We'll run each test again, and we'll get this primary up to its resonant frequency where we can gain the maximum amplitude of voltage across the primary that our function generator will push out, and then we'll go hunting for the maximum amplitude we can get on the secondary by adjusting the frequency. So obviously our little function generator here is not going to put in, or is capable of delivering, anywhere near the power that transformer is to our system, but we'll have a look and see what the effects of resonance have in the way of output from our secondary as compared to the 50 Hertz standard input and output across our secondary. Alright, thanks for watching. Next one should be pretty interesting. We're going to have to stick our inductor on a long straw and run some wires on it so we can slide it all the way through our coil here. And another question before we go that you can think about, excuse me, does the magnetic field at each end come out, curl around and go back in the same direction? So will the, say, we'll use the north and south analogy. Let's say on the top half of our AC waveform, the north field shoots out, curls around, heads down here, goes back in the south side. Is it the same for the inside of the coil? Is it the north also curls around the inside of the coil and heads on down to the south side? Another thing we'll have a look at in the next video when we slide this little inductor down there. Right, thanks for watching, and have a good night, guys.